Don't forget to subscribe and ring that bell.
There you are, back at it again, looking for some math. It is a beautiful day, third week of January in upstate New York, the Finger Lakes region. It's cloudy out, so why am I saying it's a beautiful day? Because we about to do some calculus. That's why it's a beautiful day. We are going to continue the free response section, part A. This is free response question number 2 of the practice 2014 AP Calculus AB exam. And oh, I love it. I love it. We get to use a graphing calculator. Don't get too attached. This is the last problem on the test. We get to use a calculator. Speaking of which, the TI-84 Plus CE is a fantastic calculator. I have a class set. They are boring yellow and gray. There is a whole slew of cool colors. Links in the comments below if you happen to be looking for a calculator. Personally, I own the mint green one, and I love it. Absolutely love it. Let's start. Number 2 reads, a store is having a 12-hour sale. The total number of shoppers who have entered the store T hours after the sale begins is modeled by the function S, defined by S of t equals 0.5 t to the fourth minus 16 t cubed plus 144 t squared for values of t between 0 and 12 inclusive. At time t equals 0, when the sale begins, there are no shoppers in the store, and I'm sure that's going to come into play at some point. So 2A asks, at what rate are shoppers entering the store 3 hours after the start of the sale? Okay, basics. Rate. Rate is the same thing as slope, which means derivative. Okay, so what slope or derivative? At 1 point. We want the slope at 1 point, so I am definitely going to take the derivative of the equation they give me. Now, the number of shoppers, okay, if I take the derivative, that will give me the rate at which the shoppers are entering. So this is just shoppers, okay, and remember, when we go to a rate, it's our number of shoppers per time, in this case, hour. So our answer is going to be a rate, which is going to be a number of shoppers per hour. It's not asking us to use any correct labels. I like to throw them on, though. So how do we do this? I need to find the derivative of my shoppers at time 3. And we get to use a calculator. It's not telling me that I need to show them the work. This here tells them what I'm doing to get the answer. So this is why I love using these calculators. View, detached LCD. Now, I use this calculator, and it says Silver Edition on it, but I've uploaded, okay, if you go to File, and you go to, oh my God, Open, okay, you can upload a different operating system, and this operating system is for the Color Edition. You can tell, because look at all those fancy colors, all right? Now, I want to take the derivative, math 8, okay, with respect to x in my calculator, not t because I'm using x in the calculator, of the equation they gave me for number of shoppers, 0.5x to the fourth, all right, minus 16x cubed. Okay, that's good, plus 144x squared. All right, and I want that at a value where my x, or in this case, my time is 3. I'm just going to take a quick double look. That looks like I didn't make any typos. I'm going to hit enter. And 485.99999, I'm just going to call that 486. Okay, I'm going to round up. I hope I don't got 0.999 of a shopper in that store. So I'm just going to say that is 486. Now, this is the rate. Okay, that's fine, but I'm just going to put shoppers per hour. Okay, this is my rate right at 3 hours. Right there, we're done with 2A. 2b, and this is really a good question. I like this question. Find the value of 1/3 the integral from 6 to 9 of s prime of t dt. Using correct units, okay, explain the meaning of that in the context of the problem. So your explanation is going to have shoppers involved, shoppers per hour involved, okay, because that's the context that we're using, all right? So I need to integrate. First of all, let's work on this part right here. We'll do this in blue. Okay, I need to integrate the derivative of s. Let me rewrite here what s of t actually was. 0.5 t to the fourth, okay, minus 16t cubed plus 144 t squared. This represents the number of shoppers that I currently have in the store. Okay, number of shoppers in the store. The derivative of that is, this will end up being 2t cubed minus 48t squared plus 288t. This is the number of shoppers per hour. Okay, that's a rate. So I've got to integrate this s prime of t from 6 to 9, s prime of t, this right here, dt, and then multiply that times 1/3. Now, if you have not caught on to this, this is the average value integral. What do I mean? Anytime I find an average value, okay, I'm going to scroll this down here. I integrate something. In this case, it's my rates. Okay, I'm going to integrate this rate from a lower bound and an upper bound, and I'm going to multiply it times 1 over the difference of those. Of course, 9 minus 6 is my 3. Okay, that is exactly how you find the average value of what we're integrating. So let's go ahead and find this first, and then we'll come back to this for the meaning in the context of the problem, okay? So I have something right in front of me that I need to put in a calculator. Alpha y equals, enter 1/3. The integral from 6 to 9 of, okay, the derivative of s, not s, but the derivative, 2x cubed minus 48x squared plus 288x. Don't forget the dummy variable. You cannot do any integrating without a dummy variable. Boom. Okay. 301.5. Well, you know what? No, that's good, because that's not actual shoppers. Remember, that's a rate. Okay, we don't have half a person walking around in there. Okay, so that is 301.5. 301.5. And I'm going to box that. Okay, so all I've answered is what I have in this blue box here. I found that value, 301.5. So now, using correct units. Okay, units is going to involve shoppers and hour for time, okay? Those need to be an explanation. I need to explain the meaning of this in the context of the problem, which, again, goes hand in hand with our units, shoppers per hour. So what does this mean? Before we actually put this in the calculator, we were discussing, or really I was saying, this is going to give me the average value of the rate. So this number represents the average value of rate, not shoppers, okay? It's the average value of the rate. So when I explain that, I better explain it as it's an average of the rate, not the average number of shoppers. That is important. So I'm literally going to type, well, when I say type, write, this is the average. And I better put that in there, because that's what this is all about. Okay? The average value of I'm integrating the rate, okay, of correct units and context. Shoppers entering the store from hour 6 to hour 9. Now, you could have written that with probably some less words, which I like. I like to write less. So a lot of you could have written that with 4 paragraphs. But let me explain one more thing, because I can't stand when students lose credit for not explaining right, not doing everything they're asking you to do. Okay, using correct units. Okay, shoppers, hour. Okay, shoppers per hour. And then what else did they ask us? Let's keep on going up. Context of this problem. This problem is all about shoppers entering the store. Okay, so if you don't have those tidbits in there, they have every right to take points off. But you got it in there because you're smart and you're good, and you're going to get a 5 on this exam. We're done with 2B. 2C, the rate at which shoppers leave the store is measured in shoppers per hour. Okay, it's still a rate. Okay, that should make sense because it's a rate. And is modeled by the function L, defined by L of t equals -80 plus 4,400 over t squared minus 14t plus 55. 4 times between 0 and 12 inclusive. According to this model, how many shoppers are in the store at the end of the sale, which is time 12? Give your answer to the nearest whole number, because we don't want any parts of people in the store. I walk around in the store and I see an arm laying on the ground. I'm going to get nervous, unless it's Walmart. You know, you can find people pieces down any aisle. Walmart is just that type of special place. But let's come back to the problem and get off Walmart for a second. All right? So how are we going to do this? They want the number of people. Okay, give your answer to the nearest whole number. How many shoppers? All right. Well, I got to figure out how many people are going in, and I got to figure out how many people are going out, right? Because starting at time 0, we literally have 0 people in the store. That was given to us in the initial problem. So I got to add up all the people that go in from time 0 to time 12, right? And then I got to subtract all the people that walk out of that store from time 0 to time 12. The problem is, if I have a rate of people going in, all right, or if I have a rate of people going out, I should say, this is a rate. If I have a rate, how do I get a number? Remember, this is derivative going this way. I'm going to integrate to go backward to find that number. How come I don't have to integrate the people going in? Because they gave us S of t. That's the people going in. Okay, so I can find out how many people are in that store just by plugging in my t value there. That is not a rate that they gave us initially. They gave us quantity in that. So let's figure out the number of people that are going in. This will be at 12, and subtract. Well, again, I got to integrate my people leaving from 0 to 12. Okay, does that make sense? This will give me a number of people in, and this will take my rate, and when I integrate it, will give me a number of people leaving. Right? And let's figure this out. And guess what? We have a calculator. So I'm going to take S of 12. All right? Let's go back here. And, okay, in case you didn't remember, S was that 0.5 t to the 4th minus, et cetera, et cetera. You can go back and look at that if you want. All right, so I'm going to take S of 12, which is 0.5 times my time raised to the 4th. And again, my time here is at time 12. Minus 16 times my time cubed. All right, not too bad yet. Plus 144 times my time squared. If I do this right, I get 3,456. Okay? This number here, the people coming in will be in green, is 3,456. I need to subtract my people leaving. Okay, well, we need to integrate our rate of people leaving to get the actual number of people leaving. And once I have that, I'm going to subtract that from my 3,456. Math 9. From time 0 to when we start to time 12 when we end. I need to put L of t in here. Okay, so off of this problem, they give us the following. And this is a good problem. It's, don't forget, it's negative 80. And I've got to add that to the fraction. I almost forgot the negative 80. 4,400 over x squared minus 14x plus 55. Don't forget that dummy variable. All right. This gives me the total number of people that left the store in that 12-hour period. Okay. So what I'm going to do is I'm going to take my 3,456 and subtract this number that I just got here. And you should end up with, we're going to call that 196 because we're going to round that to the nearest whole number like the problem asked us. Let's call that 3260.298. This is 3260.298. And if I do that correctly to the nearest whole number, we came up with 196 shoppers that will still be left, in the store at the end of the sale 12 hours later. 2D, and the very last problem to which we get to use a calculator, and we're going to use one for this, states. Using the given models, okay, they've given us some models, okay? They gave us S of t earlier, that's people coming in. They gave us L of t, that's people leaving, okay? But keep in mind that S of t is an actual number of people coming in. L of t was a rate at which people were leaving, okay? So there's a little difference there. So let's find the time t, okay? We got to come up with some time that's between 0 and 12, at which the number of shoppers in the store is the greatest. Okay, so we got to compare the number of people we actually have in the store. There are really two methods to do this. I will show you mine. I will explain the other way. You may do the other way. Justify your answer. That's not explaining. That's just showing your work. All right? So let's take a look at this. I know for a fact. Okay, I'm going to write this little table here. We have a function or two here that have endpoints from 0 to 12. And anytime we're going to find the which number of shoppers is the greatest. So we're looking for like a maximum number. So anytime we, here's our time, here's our number of people. Okay, anytime we check and we find a maximum, we always got to check the endpoints. Okay, so let me start with this. We know based on the very beginning of problem 2, they tell us at time 0, there are no shoppers in the store. All right? And for 2C, we just found out how many people were in the store at hour 12, at the end of the sale. And that answer was 196. That's from part C in this problem. Okay? So we know our two endpoints. Okay? So if we get a maximum number of people and it's lower than 196, okay, then 196 will be our max. But if we get a number of people in between there that's greater than 196, then that's going to be our max, okay? But here's the thing. I don't want to just look at the number of people that are in the store as I'm calculating this. I want to figure out the rate at which people are entering the store. Okay, so I want to find the rate. Notice I have a rate of the people leaving here. That's fine. Okay, but I want the rate to S of t. What was it, part B? We came up with this. It ended up being 2t cubed minus 48t squared plus 144t. That's the rate at which the rate of people entering. Okay, and I'm going to compare that to my rate of people leaving. And that was, what do we have? Negative 80 plus 4,400 over t squared. Is that minus or plus 14t? It's minus 14t plus 55. Okay? So what I like to do is I like to graph them both separately and see where they intersect. Okay? So what I'm going to do is I'm going to take S prime of t and set it equal to L prime of t. And I want to see where they intersect. As long as this function is greater or higher up on the graph than this function is, I'm getting more and more people in. The minute they intersect and my L function is bigger, that's where I'm losing people. So I want to find that point of intersection. Now, I said there's a second way that a lot of you might do this, and my son does this at his school. Okay, I teach at a different school than my son attends. Some people will just subtract this L prime of t from both sides and end up with, okay, I'm going to scroll down here, S prime of t minus L. Why did I put L prime of t? L is a rate on its own. Okay, I didn't need the prime there. L is a rate on its own. It's given to us as a rate. Okay. So I'm just going to subtract L of t. And what they'll do here is they'll find the 0 here. They'll find the x-intercept here. Okay, so if you're going to do it this way, you need to find the x-intercept. If you're going to do it this way, you need to find the intersection point. Both will be at the same thing. I like doing this way unless I absolutely have to do it the second way. Why do I like to do it that first way? Because I like to see the way they both behave. That's just my personal feelings on it. Either way gives you the correct answer. So what we're going to do here is go in our little handy-dandy calculator. We're going to turn this on, and we're going to go to y equals. And I'm going to put S prime of t in for, you know what, green is going to be the people entering. Let's color coordinate this, right? So we have 2x cubed minus 48x squared plus 144x. Okay, that's the people entering. Red is going to be the people leaving. All right, and that is negative 80 plus alpha y equals enter 4,400 over x squared minus 14x plus 55. Now my window, this sale only goes from 0 to 12 hours. So look at my window. I'm going to do this starting at time 0, because x is our time, to hour 12. Now, I'll go by ones. That's fine. Y, negative 10 is fine. This is like going to represent the rate of people entering and leaving and the difference between the two. Let's go to 400. And we'll go by 40. So we only see 10 tick marks. Okay? So if I graph this, actually, I could probably do a lot less. Let's try 200 and see if we have to move it. By 20s. Okay, let's graph this. Okay, here's the red. This is the people, wow, that going up like that. There's the red. So we are going to have to go higher. And there's the green. There we go. Oh, boy. That is a massive. Did I do something wrong here? Let me go to y equals. That looks vastly different. Negative 80 plus 40. Oh, actually, if I do this graph, where does that intersect? Yeah, I poo-pooed up. I poo-pooed up. And it looks like the green one. Let me take a look at this green one here and see what we got. Ah, I got it. And some of you might have gotten it earlier. This should be 288. 288. All right, so I was trying to do that from memory. My bad, guys. My bad. Oh, my red is still going to go out. I'm still going to have to change this window. And there's the red rate coming up. Yeah, I'm going to have to change this window big time. We might have to go to 500. Let's see. So let's go to, there it is. Go to window. Let's go to 500 by 50s. Why not? Let's graph this bad boy. Let's see if we get close. There we go. Man, that is still off the charts. Well, it's only a little bit higher. I like to see it all. I'm that particular guy. I have to go to 700 just so I can see it all. Okay, and I'm so sorry if you're still hanging with me here. Let's go to window. Let's go to 700. 700 and graph this. I'm just particular. I just call it OCD, whatever you want. There we go. Beautiful. So the red line represents our number of people that are leaving the store. Okay, and the green represents the number of people that are entering the store. So if they want us to show justification, I might sketch this. Sketch something rough of this on your paper. Now, let's do something here. Okay. Obviously, this graph right here is higher up than this graph down here. And as long as my S prime of t, okay, the green is S prime of t, okay, as long as that function is higher than my L of t, that means more people are entering. Okay, the rate is higher, so more people are entering. There's more people entering still, okay? Okay, now people are leaving now. It's not quite the same yet, but it's kind of closing the gap, right? And then until we get to this point right here. This point right here, that's where the same. Notice what happens after that point. The number of people leaving is greater than the number of people entering in, which means anything past that blue highlight, I'm going to be losing people here. Okay, these are people, I don't want that. I want the most people. So I'm gaining people, I'm gaining people, I'm gaining people, I'm gaining people up until this point. That's the time where I have the max number of shoppers in the store. So what I need to do ultimately is just find my intersection point. Where does the intersection? 1, 2, 3, 4, 5. I don't know, somewhere like right here. This is 5, this is 6. It's got to be somewhere between 5 and 6. That time is going to approximately be what? Let's go back to our graph and go second trace and pick the intersect function. And move my little spider dude close to it, whatever, and hit enter 3 times. Bang, bang, bang. And that time is 5.545. You can see the bottom left of that calculator display, 5.545. So that happens approximately at 5.545. That's it. So if I look at my table, okay, and I say, well, at time 5.545, okay, well, let's not forget, I need to make sure it's more than 196 people. If it's not, then this is my max. Okay, so what is this? I got to compare the number of shoppers. So let's go back here. 462 people in there. Absolutely. This is the number of people. This is the time that it happened. So the number of people, we'll call that 462. This is definitely when the most are in, especially when I compare it to the endpoints. That's at this time. So let's make sure we state that. Okay, let's make sure we state that. That time is 5.545 hours. That's the answer. We are done. That is 2D. We will continue and do the remaining problems without a calculator, one video per problem. Like the video, subscribe, ring the bell. And if there's something you want to see me do, a comment you want to make on something you know how to do that I don't know how to do or do differently, then leave that comment as well. Or if you have a request. I sing pretty good, kind of like Sinatra. But no, the request should be mathematical in nature. Let's not get crazy. I will see you for free response question 3. Bye-bye.
Don't forget to subscribe and ring that bell.